Hey, hi everyone. Today is day 6. I am on. There's a problem with the mic. Let's set it up. So, today is day 6 and day 5 video. I said, so there's a Sunday in between. So, I took a break on Sunday, um, which I thought I should not, but I took it, which is okay. Um, so, Saturday was day 5, but in the video I said day 4. Okay, let's get started. Let's not. So linear regression, and we were discussing about. Um, so linear regression, we were discussing about. We discussed on how the linear equation can be formed. How do we pick up certain random values for W1, W2, and for those random values, let me share my screen as well so that you guys can look at the document that we are putting together. So for linear equations for certain data set, we thought let's pick up something like this. We looked at what is the loss and what is the loss function, how do we create it and stuff, and then what is a cost function and why do we need a cost function. We have looked at this, and then yesterday we were talking about how to choose W1, W1 and W2 for the equation. So we thought we'll calculate cost for all possible W1, W2. It'll be 100 into 100, the 100 into 99. And combinations. Combinations. So this is all good. But what happens is 100 into 99, and we are still not sure that we have optimal W1 and W2 because X1 and X2 can between different values besides Y can so range between different values, and we can't determine what is the correct range of W1, W2. So what we looked at is we looked at online a three-dimensional graph where there is which has plotted W1, W2 and the corresponding cost function J. So the cost function here, we'll call it J, so that instead of every time saying cost function, we'll just refer to J, cost function, and maybe the loss function can be referred to as L. So this is loss is also called error between Y and YP, right? So yeah, this is cost function, also mean square error, MSE. And here the the absolute error of this is mean absolute error, MAE. Okay, anyways, so now we need to determine W1, W2. So imagine we got all the W1, W2s and then we put them into a graph, and we were actually discussing on how we can pick up a random point, and from there, how do you navigate down the random point to um, to figure out which is the optimal way, right? If you okay, I think people, I should not repeat everything that is there in day 5 because it will take a lot of time, but quickly bringing up on speed. So we thought like we should descend down when um, we do to in order to reach a lowest cost. Lowest cost is where you have the best possible W1, W2, and which is, that means the error is low. Lowest cost means error is low. Error is low means YP and Y are very close. YP and Y are very close means the predictions are more accurate. That's all right. So we're trying to, in within the graph, we are trying to go to the optimal cost kind of stuff. So we were actually discussing on how do you W and W2 can be varied in within the graph. It can be varied in any direction. So how do we pick up the first step and also make sure that we are traveling towards the minimum, right? So we were looking at the graph, and then for some kind of a shape that is there at that particular point, for that particular shape, we want to determine what is the in which direction should I go, right? So in order to determine the um, direction in which we need to go, so we thought we'll pick up the slope at that particular point, and slope of a curve at a single point can be calculated using differentiation. That was our discussion yesterday. So we were actually trying to look at what does the differentiation mean and all that stuff. So quick look, we can ask ChatGPT quickly on uh, asking us to explain differentiation. I think it's already did. We asked it and it already did. So if there is, so we're talking about cost function, are the actual model algorithm equation, any of the equations that we look at, if it is it is more like a specific function which has certain variables. It could be f of x is equal to something, or um, right, like w1 x1 w2 x2 is nothing but when I say function, it's more an equation which has x1 x2 as variables, where we can put in the values and then see what will be corresponding y, right? Similarly, a cost function is nothing but mean square error of y and yp, right? So it is a um, it is a function where the y and yp are put in, and then basing on that we determine what is the value of cost function. And the cost function, assuming y is always fixed, yp will vary, and in yp the varying thing is yp is nothing but equation w1 x1 plus w2 x2, in that the variables are w1 w2. So the cost function is primarily influenced by w1 w2. So the cost function j, the variables which are varying there are actually w1 w2. Agree? So that equation j, cost functions equation, is actually, which is here somewhere. There is a cost function, man, it's not here. Yeah, here, this one. This is mean square error cost function. So this equation, if you look at it, so differentiation of the right side equation will give slope of this particular graph. If you draw a graph of this particular equation, whatever you get, the other day you looked at it, that graph, in order to look at a slope at a certain point of this equation, if you differentiate this particular equation, you get the slope of the um, equation, correct? So differentiation, um, okay, just sorry guys, I was actually thinking on what is a better way to explain it, but so differential gives slope, and then the slope gives us the direction in which the particular line is going. For example, if you take it to that particular line, at that particular point it would draw a line like this. Okay, so what does this line indicate is, and basing on the curve the line will change. Okay, so what happens to this line and to this point, it will draw a line, okay, which actually is parallel to that particular point. um, to detail on little bit on differentiation, right? So differentiation is calculated saying in this w1 w2 that is there in this particular equation, if I change w1 w2 a little bit, how does the function vary? Like how much does it vary? The cost function, like w1 w2, if I change it by a little bit, like plus 0.0001 and w2 by plus 0.001, if I vary them, how much does the cost function vary? That is actually how a small difference that is created in the input, how much difference does it create on the function, it is cost, is what is the main thought process of calculating differentiation, right? So um, once you get the slope, then it says okay, that is the amount of difference it would make for a small change in w1 w2 is what we understand in the cost function. So that particular differentiation, we would apply it saying okay, that shows that this is the direction it is going. So the particular differentiation we would use as a metric on the amount of change that we want to give to w1, so that it changes in this direction. So w1, if you remember, if you in a given graph, if you are here at w1, you can actually don't know that the lines are like this, right? Because these are all not calculated, you are only here. So once you are here, you can go this way long, or you can go that way. You can go from this point that you see here, it can go in any direction. But in order to go down the to the possible point which goes down, we should pick up w1 w2 in that direction. So if you see w1 w2, if you differentiate, the w1 w2 will be somewhere here, and we should go to this step, to that step. So w1 minus the differentiation is the line that it is drawn like this. It gives you the next step on that particular slope, correct? Because the line is drawn like this from that point, correct? So you pick up that point next. To pick up that point, um, from the cost, what is the difference on w1 w2 is the differentiation. The differentiation gives us what is the value of what is the value to which w1 w2 should be changed, so that it actually takes you down the particular slope. So what we do to pick up the next value of w1 w2, that is the new w1 w2 will be w1 w1 1 maybe, and w1 1 and w1 2 1, let's say, is equal to w1 minus the differentiation that we have. That's how we calculate. Okay, this is logistic equation, so here we should be here. Gradient descent differentiation to reduce w1. And descent is iterative optimization algorithm used. Suppose we can. So as I said, w0, w1 are actually the variables in the mean square error, and those actually impact the cost function, which is mean square error. Instead of saying cost function, is saying mean square error. So what he says is the new value of w1 is equal to w1 minus alpha of differential of mean square error, this equation, by w1. That derivation by w1 is used in order to reduce w1, so that within that slope we make sure that w1 is going down that particular slope, right? Similarly, w2, if it is for us, w2 is also that w2 is equal to w2 minus um, differential of W2 into mean square error. So when I said differential, I said it's a minute step, right? It could be 0.001 or something like that. So in that particular slope direction. What is this alpha that you see here is we want to go down, but at the same time we want to I mean, maybe people were actually going down like that to get to the local optimal value of cost function, so that we have a good algorithm or model which can predict yp, which can predict y. So then what happened, still basing on the initial w1 w2 and basing on this steps, what happens if the curve is like this, if you are here and the optimal path is here, it would not be a straight line like that, but just imagine if you are here at this point and then you need to travel all this way like this, right? So how do you come faster to this is the best approach, agree? So what happens, the way you pick up w1 w2, that's one thing. Second thing is the steps that you take. For example, if you take small steps like this, it will take a lot of time. So but if you take bigger steps, you can come faster, right? But there is also a possibility, what happens is this graph, it could be like this, right? You are here and it could be the local optimal, and again it might increase. If you pick up something much bigger, what happens, you go this big, and then you'll come here. So and then, but your local optimal is here. So these the changes that we make to w1 w2 um, are are basing on the differential of that particular, so that we are going through the slope. But at the same time, we don't want to take that small steps, we want to increase it, but how much we increase it is driven by this alpha. So we multiply the saying, instead of moving 0.001 at one time into 5, let's say our learning rate is 5, then move 0.05 and then make the steps, so it is a little faster. So that's how the w1 w2 is varied. Let us look at image linear regression, no, gradient descent image with steps, let's say. So instead of that complex curve, what they did is they were actually explaining it with they're putting it on a graph like this, right? Like this is the cost function, these are weights, like this is j, and this is weights w1 w2. So if you look at it, what happens, let's say we picked up w1 w2 here, and then he picked up the slope, and then we pick up the next step, right? And then we keep growing until we reach this, right? So I think it will also explain on what is the impact of picking up a small alpha to huge bigger alpha as well. Yeah, so if we go like this, what happens if your learning rate is too small, you're doing steps like this, so many, right? It takes a lot of time. But if you give a little bit, then what happens, from that stage you pick up steps like this, okay? But if you look at it, what is happening, there is another variant. I mean, it's too early to discuss, but what is the ways people are actually thinking, okay, how do I know what is a big alpha, what is a small alpha, kind of stuff, right? So um, they have come up with one more approach, which is interesting, because what happens, right, as I told you guys, it's not like one day's thing or 2 days thinking. It's like people, like as if I'm thinking, right? People think through this process and then they see, okay, how do, still it takes more compute. Those days, actually, today, if somebody would have done, they would not have spent so much time on optimizing it, because back then, when initial linear regression is invented and stuff, the computes were slow. The resources that the hardware has were low. So we need to be more optimal. The more optimal we can have an algorithm which can efficiently process more data. Considering all that, they were actually continuously optimizing that particular thing. And I'm sure all these each one of thing that we are thinking through and stuff is these people would have thought through. They would have published it, each change that we're talking about, right from loss function to cost function to um, calculating the slope and taking the descent, right? Descent. And how do we take the descent? Descent is through differentiation. Differentiation is nothing but gradient. So so this gradient based descent. And after that, how do you optimize it? Instead of taking the baby steps, you can use something called learning rate and make a difference on how much steps you make. So how do you pick up learning rate? It should be uh, what happens if the learning rate is very small, or if the learning rate is very big. All that is done, and one of the optimizations that they brought in after series of steps is the alpha rate. Instead of being static continuously when you're descending, they thought they could make it dynamic, where it would we would pick it relatively. I will not get into the details on how we can relatively pick up an alpha rate. Alpha means learning rate. um, but it would technically decrease, so that the initial steps, as you see in this image, the initial steps from the starting point will be higher, and when you come closer to the convergence, it'll get smaller and stuff. So that if you go with this path, what happens here, it could come here, or it could come here, and then it could take a jump here, and it'll cross, it'll keep going up, and you might not reach you'll miss the convergence, right? That you see here on the screen here. Sorry. So what we need to do, we start off with a bigger jump. The bigger jump is driven by big alpha, and we keep reducing the alpha as we reduce the cost, in a way that it would actually take baby steps when it goes to the last piece, so that the point it could reach a specific point, or else even if it is this size, what would happen from here, it would go here. That means it is missing the actual optimal way. And even though it looks like a small thing, when you calculate the difference in cost of being here to being here, that would in turn, if you boil down, that cost variation in turn reduces your algorithm's capability of predicting YP properly. So imagine even a 1% difference means 1% error means you have 1 million records, and or let's say even simple number 10,000 records, and almost you have 100 records, 1% 100 records, the uh, where your values are wrong. YP and YP are wrong. So which is impactful thing, right? So um, the optimal is very important. That's what I'm trying to say with respect to picking up this learning rate and stuff. So that's the um, going back on here. He explains on how W1 and W2 can be reduced using this particular differentiation and stuff. So now we are clear. We pick up a random W1, W2. We use this particular equation and calculate cost. We to look at what is the cost there, and we pick up the next points. So another indicator is, how do you know that we reach the bottom, right? It's I think it's simple, within this graph. So from here also you'll keep going. Nobody knows that's it's a minimal point, because he doesn't know this, right? Whether this is going upwards, going downwards and stuff. This is all future. Only thing that you know is you come to this point, then you calculate cost, so you know this cost. Otherwise, this all is future when predicted. So what happens, people, when the algorithm is ran and when you do this gradient descent, you do calculate the next step. If the next step is increasing, that is when you decide saying, okay, so the next steps are increasing, This should be the optimal point to which I should actually go, right? I mean, ideally, even if you look at differentiation of that particular, the slope will also be minimal. So your differentiation term that you use W1 minus, that will also be minimal. So the W1 change will also be very, very small, and that gives you an indication saying you reach the optimal point. Correct. So that's it with the linear regression. We're supposed to do it in one day, uh, and we have dragged it to 3 days. But I believe you guys understood what's a what's a linear regression, what is an equation, how do you look at what is the objective of creating an equation to identify patterns and stuff, and then how do you predict values as YP, how do you look at loss, how do you make it absolute error, why do you need to make it mean, and then why do you need to go for a cost function which is nothing but a mean square error, where you square the we do a mean of squares of the differences between y predicted and y, which is called as the error, and basing on cost, working backwards, the initial equation which has w1 w2 variables, basing on the cost, how do you pick up what's your next w1 w2. So and you go through this loop of picking up multiple w1 w2s as you see here, until you reach this yellow point, which is the optimal w1 w2 with the minimum cost, right? So that's all. This is all linear regression is. The complexity grows much higher and higher. You have more features, you have more w1 w2 w3 w4 and stuff, and then calculating, doing and stuff will be complicated. But as the machine is doing it, we don't sit and do this math on our own. The machine is doing it. Machine is capable of doing computation in parallel much faster and stuff. So it works in a pretty decent way, right? So there are more concepts to discuss, but I'll try to cover them in the next thing. So let's move to the next big thing, that is logistic regression. So logistic regression is more a binary classification problem. When I say binary algorithm, it's not a problem, it's an algorithm, it's actually a solution. So binary classification, when I say binary is 0 1, classification is classifying is to segregate on what kind it is. So binary classification term means you pick up two kinds, 0 and 1, and then you classify with saying whether it is 0 or 1. That's all. Right? That's binary classification. These terms actually sound complicated, but if you understand the meaning of it, is very simple. So um, few people name keep meaningful names so that people actually read that name and understand what it means. So um, but what if there are like whether it is a car or a bus, it's an apple or orange, those are all binary classifications where you to make two. How about you have multiple choices, whether is it a bike, or is it a car, or it's a bus. So this is multi classification, where you can have multiple more than two kind of, so it can be three, four, five, how much ever it may be. So using logistic regression, we can't achieve that multi classification directly, but indirectly you can do. That means what you do, you classify them in parts. So you use multiple models. One, what you'll do, you'll start off with, is it bike or not a bike. So rest all is one category, and you can classify like that. So you pick up all bikes, and these are all not bikes. Within not bikes, you again take it in input, and you create another model, and you say, is it a car or not a car. Then you say, is it a bus or not a bus. Like, I mean, obviously, if there are only three, anything not a bike, not a car will become bus. But I'm just saying, you can keep going like that with multiple classifications. So previous model, what's the difference between linear regression and logistic regression is, linear regression is where you actually are predicting YP. And if you look at our document, YP can be anything, right? It can be random numbers of different range. Now he said 5, 10, 20, 50, like we predicted 6, 12, 24, 18, minus 18. But let's say it's something like predicted house value, for example. Then predicted house value is could be in thousands, right? It could be like 300,000 800,000, something like that. So the number could go bigger. Like if you're predicting something like um, market value of a company, a bigger company or something, that could vary from few millions to billions or something like that. So the numbers could vary, and the numbers, if they are varying like that, we would usually, that varying output is called regression. Okay. But whereas logistic regression, whereas classification is where you know what is the output, what are the possible outputs that are there, and we try to fit in the output into this particular possible outputs that are there. Sorry, let's say multi-class classification, you can call it like 0, 1, 2, 3, and you need to, the output should be either 0, R1, R2, R3. So let's start off with binary classification, where the output should be 0 and 1. The one which you have here, the linear regression, it is giving you incremental numbers. So they thought, but the output that we need is 0 and 1. So and as I said, most of the algorithms, the underlying basics is on linear regression. So what they did, okay, let me do linear regression, but whatever value comes in linear regression, I want it to be um, oh, I want that linear regression value to be set into 0 and 1. Means it would say, if my output of linear regression is 5 or 6, then I am 0. If it is 24, then it is 1. Like that, basing on the linear regression value, I can classify and say 0 and 1 kind of stuff. So basing on the input numbers that are there, I would classify and say this is 0, this is 1 kind of stuff. So to achieve it, they came up with what is an equation which can take this value output, that is the algorithm that we used here, this one, yp, which gives me a regression value like this, and convert it into, which is a classification where it tells me whether it is 0 or 1 kind of stuff. When I say it tells 0 or 1, it usually, the value doesn't say exactly 0, exactly 1. The good part is it would actually give us a value in between 0.05, and usually we would consider anything between 0.05 towards 0. It would say 0.5 to 1, and that we will consider as 1 kind of stuff. So um, which actually gives the probability, how much probability it has of becoming 0, or how much probability it has of becoming 1. So let's say you get 0.3, that means for probability of 0, if you get 0.3, that means probability of becoming 0 is 0.3, and probability of becoming 1 is 0.7. So the more it was towards 1, so we think it would go to 1. But when you give the output, the algorithm says actually, like, it could be 1, like let's say apple and orange, it could be orange with a probability of 70%. So still it tells you 30% it might not be an orange, it might be apple, or something else that could also. But imagining there is only two fruits in that particular basket, either apple or orange, so 70% I'm sure this is orange, but 30% it could be apple as well. So that's how the logistic regression output output would be. So we are thinking on how can a value be, even though it has varying values like this, how do I put it into an equation, and that equation is giving from 0 to 1. I told the same point 10 times, I know, which is not nice, but they came up with something, some equation. So the logistic regression, the formula. So they use something called sigmoid function. Why did they pick sigmoid function? Again, it's more, it's more applying maths to solve the problem. So what they want is 0 to 1, and what they looked at is which mathematical equation is the one which will take me to 0, um, to that range of 0 comma 1. And they've the mathematicians know that it's sigmoid function. Okay, let's look at the graph of sigmoid function. If you look at it quickly, you can understand why they picked up sigmoid function instead of there could be several functions, and why did they pick up sigmoid function? So a sigmoid function graph looks like this. Okay, so it would go very close to 0, and the center value will be 0.5, and then it goes to 1. So this is perfect, right? Like, so then what we'll do, let's say 0 is apple, 1 is orange. um, then what happens is anything between 0 to 0.5 we can call it apple, 0.5 to 1 we can call it orange. So that's the kind of output that we are looking at. And sigmoid function, the way it is perfectly fitting in like that, right? Like it starts off with values less than 0.5 and travels all the way between 1. So it's somewhere in between 0 and 1. This is this they understood this is the perfect fit for how the sigmoid function would be. And sigmoid function, as they know, the equation is 1 plus 1 by 1 plus e power minus x. That's the thing. Instead of x, what we did, so we take points, we create linear regression. The linear regression's output that is there, that is yp. Instead of calling it yp, they are calling it z here, if you see. And that z they are putting into here, it is minus z. So what is the value of z is c, w0 plus w1 plus x plus w2x plus this is nothing but our linear regression equation. So linear regression equation is done. You calculate z, and then you put it into the sigmoid function 1 by 1 plus e power minus z, and that will give us the probability of for the particular classification. Correct? Got it. Okay, let's ask actually, why did they pick sigmoid? Function logistic regression is motivated by several desirable properties. One is output range. Monotonicity, there is monotonically increasing, meaning that as an input z increases, the output probability also increases similarly as z decreases. This property ensures that change in the input features correspond to predictable changes in smoothness. The sigmoid function is smooth and differentiable everywhere, which facilitates optimization. Sigmoid's derivative is sigmoid function. Let's say we call it sigma. Sigma is sigma if it's differentiated. He's saying the differentiation is sigma of 1 minus sigma. I would love to do actually the math to show you how the differentiation of 1 by 1 plus e minus z will work. But I think this time I'll step back. I'll compromise saying I'll put it outside the scope of this discussion. But I did it when I'm studying it, and you guys can also do it. So all you need to do understand is differentiation of e power x. If e power x is differentiated, what do you do with that kind of stuff? So that boils down to 1 by 1 plus e power minus z. How do you differentiate it kind of stuff? You should give it a try. So that's how the sigmoid function is discussed. It is, I think, in line with what we were discussing. So same logic as we did in linear regression. So linear regression, y and yp is the output. And so what we did, we calculated loss in between yp and y, and then we calculated cost as well. Basing on cost, we were changing w1 w2. But whereas logistic regression, it is two steps, right? Like you get the x1 x2, you put it into the regression equation, w0 w1 x1 kind of stuff, and then you put it again into sigmoid function, and then you get the output. So your output is not yp. Now it is, your output is actually yp, which is put into a sigmoid function kind of stuff, right? So Now, how do you calculate cost? Because here what happens in the cost function, your cost function is actually um, predicted value, that is like apple is 0 and orange is 1. And if your predictions are somewhere in between 0 to 1, using because it's a sigmoid function, if you do difference of them, say 0 minus 0 0, 1 minus 1 0, so it's like um, that's how it will be, right? Like, so like let's say if it's 0.5, then it is minus 0 minus 0.5. If you're trying to predict at 0.3, and if it's an orange and you get 0.3, then 1 minus 0.3, that's you're supposed to be 1, but your actual value is 0.3 for apple. For orange, then the error is 0.7, right? 1 minus 0.3. That's how you should differentiate. So to do this differentiation, they came up with a loss function. I would love to derive this loss function, and it makes complete sense. Um, so sigma is the sum of losses across all the records, correct? And we are doing a mean. So and if you see, we're not doing any square here, because our values are always in between 0 to 1, right? Like anything, the loss should be within that. So um, there's no need for amplifying it or something like that. But if you look at it, if you in this scenario, yi is the prediction, right, on what it is, kind of stuff. So yi could be in 0 to 0.5 or 0.5 to 1. I'm just thinking, when they put in yi, um, do they keep um, let me see once again. This is a good question to ask. And it's nothing wrong actually. If you I remember looking at it, but I just want to reconfirm saying whether the yi that we see here in the last function, is it something like this 0.5, or is it going to be, which corresponds to z is equal to 0, um, or should it be the 0 and 1? I remember it should be 0 and 1. That's the logic, but I'll cross check on it. Maybe I'll give that detail tomorrow, um, which is okay. I can look up now also, but instead of interest of time, I'm not looking up now. But let's assume it's 0 and 1. Then what happens? If it is 0, then the loss is very simple. 0, this becomes whole 0, this becomes 1. Then the loss is log of 1 minus y. Okay. Um, if it is 1, then this becomes 0, and this becomes log of y. Correct. So yeah, so here you can actually see the difference. Um, Basing on the output value, like whether y is 0 or 1, we pick up the loss. The loss is subjective. Okay. The loss is possibly two values, either it's log y or log 1 minus y. And when is it log y? When the y is 1, it is log y. And when y is 0, the loss is log 1 minus y. Okay. So in order to accommodate it, they have put together this equation. Both y and 1 minus y multiplied, so that you get the only that specific value, either log y or log 1 minus y. You get the corresponding value basing on the y that we are trying to predict. For zeros, this one. For all zeros, this one. For all ones, this one. And is um, yi is definitely not 0 comma 1, the one which we are discussing previously, right? It's not 0 comma 1. It varies, and um, basing on how it varies, it is sorry, one second. Basing on how it varies, it will um, it will give a specific value out of it, the logarithm of that particular value. For example, log of 0.5 on either sides, because 0.5 is one place where both sides are possible, so the loss will be same. Log of 0.5, either if y is equal to 1, log of 0.5. If y is equal to 0, also 1 minus 0, log of 1 minus 0.5 is again log 0.5. So the loss is same, 0.5. Similarly, it will keep varying based on the different values of the predicted outputs. Correct. That's the loss function with logistic regression. I should have completed logistic regression value today, but I somehow feel we are squeezing in too much things into it. So I would like to take a break here, and I'll revisit logistic regression in much more detail um, tomorrow. Okay. Thanks, guys. Stop presentation. Bye, and end of stream.